everyone, and welcome back for another deep dive. Today we'll be looking at the physics of pendulum.
Pendulum.
Well, not the typical back and forth kind.
Okay.
We're going 3D with these pendulums. Our source material for this deep dive is Open Educational Resources, Open Source Physics at Singapore.
Sounds cool.
It is, and get ready because this one's going to make you think about pendulums in a whole new light.
So what makes these 3D pendulums so special? I mean, we all know what a regular pendulum does.
Right, but instead of just swinging back and forth in a single plane,
Yeah.
a 3D pendulum can swing in any direction.
Oh, wow. So it can go in like a circle or even a spiral.
Exactly. It's like it's tracing out a sphere as it moves.
I'm trying to picture that in my head.
Okay, so picture a weight hanging from a fixed point.
Okay, got it.
To describe its position, we need two angles, not just one like with a regular pendulum.
Oh, because it's moving in 3 dimensions.
Exactly.
Yeah.
We use theta to measure how far the pendulum is from hanging straight down.
Okay, that makes sense.
Yeah. And then we use phi to tell us the direction it's pointing from above.
So it's like we're pinpointing a location on a globe. We need 2 coordinates.
You got it. And of course, we also need to consider the pendulum's speed.
So how fast those angles are changing, the angular velocity.
Right. And I'm guessing this is where things start to get a little more complex, right? I mean, we're dealing with forces and motion and all that good stuff.
You're right. There are some serious physics equations involved.
Equations.
But don't worry, we don't need to get bogged down in the math here.
Oh, good.
The main thing to understand is that physicists use something called the Lagrange equation to analyze how this 3D pendulum moves.
Lagrange equation, that sounds intense.
It is a pretty powerful tool. It helps us understand how all the forces, gravity, the tension in the string, and the pendulum's momentum all work together.
So it's not just about where the pendulum is, but how all those forces are making it move.
Right.
Okay, well, the source material also mentions something called a circular loop checkbox in a simulation of this pendulum.
Oh, yeah, that's a cool one.
What happens when we check that box?
Basically, it forces the pendulum to move in a perfect circle.
Whoa, hold on. So it stops swinging back and forth.
Yep, the back and forth motion, that swinging, stops completely and it just moves in a circle.
But why doesn't it just fly off in some random direction?
That's where the idea of centripetal force comes in.
Okay, I've heard of that, but remind me.
It's the force that pulls an object towards the center of a circle, keeping it moving in that circular path.
So like when you spin a ball on a string.
Exactly. The tension in the string is providing the centripetal force.
Oh, I see. So in this circular loop pendulum, the tension in the string is what keeps it moving in that perfect circle.
You got it.
But wait a minute, isn't that the same force that keeps satellites in orbit around the Earth?
You're exactly right. The reason a satellite stays in orbit is fundamentally similar to why this pendulum swings in a circle. It's all about balancing forces.
Whoa, mind blown. So we've got this pendulum moving in a perfect circle when that circular loop box is checked. What happens when we uncheck it? Does it just go haywire?
Things definitely get a bit more unpredictable when we uncheck that box.
Okay, how so?
Well, now the pendulum's height can change as it swings, so it's not stuck in that flat circle anymore.
So instead of a perfect circle, it might start doing like a crazy spiral in 3 dimensions.
Exactly. And it can get even crazier if you start changing the time it takes for the pendulum to swing back and forth.
Oh, interesting. So by messing with the period of the pendulum, things get more chaotic. But how does changing the period even come into play here?
Remember those angular velocities we talked about, how fast the angles are changing?
Yeah.
Well, the period is tied to those angular velocities.
Oh, I see.
So if you change one, you affect the other.
It's all connected.
And since those angular velocities are part of the equations that describe how the pendulum moves,
Yeah.
any change to them affects the whole system.
So it's like a chain reaction.
Exactly.
Yeah.
Mess with one thing and the whole delicate balance gets thrown off.
This is fascinating. The source material also mentions that you can change the length of the pendulum in the simulation.
Oh, yeah. That's where things get really interesting.
What happens when we do that?
Well, remember those equations of motion we were talking about?
Vaguely.
Well, the length of the pendulum is a key factor in those equations.
Okay, so changing the length changes how the pendulum moves.
Absolutely. For example, if we make the pendulum longer, gravity has more leverage, pulling on it with more force.
So it swings more slowly.
Exactly. And it also swings further out from its resting point.
It's like pushing a kid on a swing, right? The higher the swing goes, the longer it takes to swing back and forth.
That's a great analogy.
Mm-hmm.
And the opposite is true too. If you shorten the pendulum, the swing becomes faster and the arc gets tighter.
So essentially by changing the length, we're manipulating the pendulum's period, right? that time it takes for one complete swing.
Exactly. And remember, that period is tied to those angular velocities, so those change as well.
It's all connected.
It is. It's all a delicate balance between gravity, the length of the string, and the tension in the string.
This makes me think about all the different kinds of pendulums out in the world, like grandfather clocks or those giant swinging amusement park rides.
Oh, absolutely. The length of those pendulums is carefully calculated to get a very specific effect.
Yeah, like in a grandfather clock, the length is crucial for keeping accurate time.
Exactly. And in those amusement park rides, they use varying pendulum lengths to create those thrilling swinging motions.
So understanding these concepts actually has real-world applications.
You got it.
This deep dive is really opening my eyes to the physics all around us.
Me too.
It seems like something as simple as a pendulum can teach us so much about the fundamental principles of the universe.
It really can.
But before we move on, I want to circle back to that circular loop scenario for a second.
Sure.
You said the tension in the string provides the centripetal force to keep the pendulum moving in a circle.
Right.
What happens to that force when we change the pendulum's length?
That's a great question. Remember, the amount of centripetal force needed for circular motion depends on both the speed and the radius of the circle.
Okay.
And when we change the length of the pendulum, we're changing the radius of that circle.
Ah, that makes sense. So to keep the pendulum moving in a circle, something has to change, right?
Exactly. The tension in the string has to adjust to provide the right amount of centripetal force for that new circle.
So if we lengthen the pendulum, we need more tension.
Right. And shortening it means we need less tension.
It's all about maintaining that delicate balance, huh?
It is. It's amazing how these seemingly small changes to the system can have such big effects.
This is all starting to click into place now.
Good.
It's fascinating how even slight changes to a simple system like a pendulum can have such a big impact on how it behaves.
It is, and that's the beauty of physics, uncovering the underlying principles that govern the world around us.
I love that from a pendulum to the planets in our solar system, it's all connected. Speaking of which, I feel like we've mainly been focusing on the pendulum itself. But our source material also mentions this interactive simulation.
Oh yeah, it's really cool.
Can you tell us a bit more about that?
Absolutely. The simulation allows you to play with all the variables we've been talking about.
Oh, cool. So we can change the angles and the length and all that.
Yep. You can adjust the angles, the angular velocities, the length of the pendulum. You can even play with that circular loop checkbox.
That sounds awesome. It's one thing to talk about these concepts, but to actually see them in action must be really helpful.
It is. It's a great way to visualize everything and get a more intuitive feel for how it all works.
I'm a big believer in hands-on learning, so I bet that simulation is super useful.
Oh, it definitely is.
We'll make sure to include a link to it in the show notes for anyone who wants to check it out.
Good idea.
But before we send everyone off to that digital playground, I think it's time to zoom out a bit and consider the bigger picture.
I agree. It's important to see how this all connects back to the real world.
Exactly. So we've spent all this time talking about pendulums. Why should anyone care about the physics of this seemingly simple system?
That's where it gets really exciting. You see, understanding how a pendulum works can actually help us understand all sorts of other systems, from the motion of planets and satellites to the way bridges and buildings oscillate.
Wait, are you serious? So the same principles that govern our little pendulum apply to massive structures like bridges.
It's true. Bridges, for example, can experience oscillations due to things like wind or traffic.
I can imagine.
And understanding the physics of pendulums can help engineers design bridges that are more stable and resistant to those forces.
That's incredible. It's amazing how these seemingly different phenomena are all connected by the same underlying physical laws.
It really is. It's like there's this hidden language of the universe, and we're just starting to decode it.
I love that analogy. And that's just one example, right? We also see these principles at work in things like metronomes used by musicians and those swinging amusement park rides we talked about earlier.
Exactly. And even the motion of planets around the sun can be understood through the lens of these basic physics concepts.
Wow. It really is incredible how much we can learn from something as simple as a pendulum.
It is.
But I feel like there's still one piece of the puzzle missing here.
Oh,
Remember that part in the simulation where you can drag the blue dot to change the pendulum's length?
yeah.
We haven't really talked about that yet.
You're right. We can't leave everyone hanging on that one.
Exactly. Let's delve into that in part 2 of our deep dive.
Sounds good to me.
Stay tuned, folks. We'll be right back after a short break. All right, we're back and ready to tackle that dragging the blue dot mystery.
Mystery. I wouldn't call it a mystery. It's more like a cool feature that lets you see how changing the pendulum's length affects everything.
Fair enough. So walk us through it. We're in the simulation. We see that blue dot representing the pendulum's weight. What happens when we start dragging it around?
Okay, so imagine the pendulum is swinging, doing its thing, maybe a nice back and forth or that perfect circle.
Got it.
Now, picture yourself slowly dragging that blue dot downwards, like you're making the string longer and longer.
Okay, I'm seeing it in my mind's eye. I feel like the swing would get wider, like you're giving it more space to move.
Exactly. As the pendulum gets longer, gravity's pull on it increases, so it swings more slowly.
Makes sense. Like it has further to travel, so it takes longer.
Right, and it also swings further out from that center point.
Oh, I see. So it's like pushing someone on a swing. The higher they go, the longer it takes to swing back and forth.
Perfect analogy. And now think about doing the opposite.
Okay, so we grab that blue dot and pull it upwards, shortening the string.
Yep. Now what do you think happens?
Well, if making it longer slows it down, I guess making it shorter would speed things up.
Exactly. The pendulum will swing faster, and that arc, that path it follows, gets tighter.
So it's like we're manipulating time itself. I mean, we're changing the period, the time for one complete swing just by messing with the length.
You got it. And remember how we said the period is connected to those angular velocities? Those are changing too.
Right, because we're changing the balance of all those forces acting on the pendulum.
Exactly. It's all about finding that sweet spot where everything works together perfectly.
And this reminds me of what we were talking about earlier with grandfather clocks and how they need that specific pendulum length for accuracy.
It's a perfect example. Clockmakers have to get that length just right, so the pendulum swings with a period of exactly 1 second.
Whoa, so each swing matches a tick of the clock.
Yep. Pretty cool, right?
It is. It's amazing how much precision goes into something like that, and all thanks to the physics of pendulums.
Absolutely.
You know, this is making me realize just how many real-world applications there are for these concepts.
It's everywhere. You see it in bridges, amusement park rides, even the way a metronome keeps time for musicians.
It's like we're surrounded by pendulums, even if we don't always realize it.
Exactly. And it all comes back to those fundamental laws of physics that govern how things move and interact.
It's mind-blowing when you think about it like that. It's like we've uncovered this hidden world of forces and motion that's been right in front of us all along.
And the best part is we're just scratching the surface. There's so much more to explore when it comes to the physics of pendulums and beyond.
Couldn't agree more. I think it's time to wrap up this deep dive. Any final thoughts you want to leave our listeners with?
Well, I'd just say keep your eyes peeled for those pendulum principles in action out in the real world. You might be surprised by how much you start to notice once you know what to look for.
That's great advice. Thanks so much for joining us on this incredible journey into the world of 3D pendulums.
My pleasure. It's always fun to dive into these fascinating topics.
To all our listeners out there, thanks for tuning in, and until next time, keep exploring and keep asking those curious questions. All right, welcome back everyone for the thrilling conclusion of our pendulum adventure. We left off talking about that dragging the blue dot thing in the simulation.
Right, yeah.
So we can change the length of the pendulum on the fly. I'm really curious to see how that affects everything.
Well, it might seem like a small change, but it can have a huge impact.
Okay, so let's say we're in the simulation looking at the pendulum and that blue dot representing the weight.
Okay.
We click and drag it, making the string longer. What happens?
So think about it this way. The longer the pendulum gets, the stronger gravity's pull on it becomes.
Right, so it swings more slowly.
Yep. And it also swings further out from that resting point.
Okay, makes sense. So like if it was swinging back and forth before, the arc would just get wider and wider.
Exactly. And the opposite happens if you shorten the pendulum. The swing gets faster and the arc gets tighter.
So it's like we're directly controlling how fast or slow the pendulum swings just by changing its length.
You got it.
And of course, this all ties back to those angular velocities and the period, right?
Absolutely. Changing the length messes with the whole balance of forces, which forces those other things to change too.
It's all connected.
It is. It's all a delicate dance between gravity, the length, and the tension in the string.
And this is exactly what clockmakers have to consider when they're designing those super precise grandfather clocks right.
You know it. They have to get that pendulum length just right, so it swings with a period of exactly 1 second.
Wow, that's amazing. I never realized there was so much physics involved in something as simple as a clock.
There is, you'd be surprised. And it's not just clocks either.
Oh, right. We talked about bridges and amusement park rides, too.
Right. The same principles apply to all sorts of things. It's all about understanding how forces and motion work together.
And the best part is we can actually see these principles in action in the real world.
That's what makes physics so cool. It's not just some abstract theory, it's happening all around us.
This has been such an eye-opening deep dive. I feel like I have a whole new appreciation for the physics of pendulums now.
Me too.
Mm.
It's always fun to explore these topics and see how much we can learn from something as seemingly simple as a pendulum.
And to all our listeners out there, thank you so much for joining us on this journey. We hope you enjoyed it as much as we did. And until next time, keep exploring the world with those curious minds of yours because you never know what amazing discoveries you might make.